Hi everyone, in this video I'll be talking about the Wilcoxon-Mann-Whitney test and doing an example of this test. As a reminder, the Wilcoxon-Mann-Whitney test is basically the non-parametric alternative to the t-test for comparing two populations. In the Wilcoxon-Mann-Whitney test, you don't have any of the assumptions that are required for the t-test, namely that the population has a normal distribution or that the sample size is large. So when you find yourself with data that is not necessarily normal and a small sample size, and you want to compare two populations, then the Wilcoxon-Mann-Whitney test is a great candidate for your analysis. Okay, so here's our example problem. It's from your book. It's about a study comparing the respiratory responses of hypnotized and non-hypnotized subjects. There were 16 volunteers. They were allocated either to the experimental group or the experimental group or the control group. And there were measurements taken at the start of the experiment, and the researchers seemed to think that the breathing patterns were different between these two groups, and they were speculating that maybe it's because the hypnotized people or the people who are going to be hypnotized were anticipating this and kind of excited about it, and so maybe they had different breathing patterns as a result. So we could think of the null hypothesis as the distribution of breathing patterns is the same in both groups, or compare that against the alternative hypothesis, these distributions are different from each other. Distributions are different. Okay, so that's the null hypothesis and the alternative hypothesis that we can use here. Notice that I did not mention anything about a population mean. That's a parameter, and this is a non-parametric test. So we're talking about the distributions generally, whether they are the same or they are different. So the data that we're looking at is in this table. We have an experimental group and a control group. And although we have 8 observations in the experimental group and 8 observations in the control group, this is not paired data. It would be paired if those were the same subjects that were maybe measured at 2 different times, but that's not what's happening here. We have 8 completely different subjects. These are independent samples. And so initially we might want to be able to use a t-test on this, but we don't know that the data is normal, or that we believe that it can be assumed that the data is normally distributed. We also have a very small sample size. There's only 8 people in each group. So we're going to use a non-parametric approach for this problem, the Wilcoxon-Mann-Whitney test. So the way this test works is you're going to set up a couple of new columns with your data here. So that's what I recommend you guys do. So to the left, I'm going to put this column called number of control observations that are smaller. So the left column being the experimental column, I'm going to want to go down every row on this experimental column and count up how many observations in the other column are smaller than that number. And similarly, I'm going to do the same thing on the right side, the number of experimental observations that are smaller. All right, so let me show you how this works. So first of all, you should notice that they have conveniently already arranged the observations here from smallest to largest in both categories, and that's going to help us. So the first thing we're going to say is, okay, we'll look at this 5.32 and we'll see how many of the control observations are smaller than 5.32. We have this one, this one, this one, this one. And then 5.41 is obviously greater than 5.32. So we have 4 observations that are smaller than 5.32. Then let's look at the next one, 5.60. How many are smaller than it? 1, 2, 3, 4, 5 are smaller than 5.60. So we'll put 5 here in this row. And we're going to keep doing the same thing. So 5.74, 1, 2, 3, 4, 5, 6. 6 of them are smaller than 5.74. And then 6.06, 1, 2, 3, 4, 5, 6, still 6. And then 6.32, that's bigger than all 8 of them. So I can put 8 here, and I'm going to be able to put it for all the remaining ones. Now we're going to do the same thing on the other side. We're going to look at the control observations and say how many of the experimental observations are smaller than each one in the control column. So starting with 4.50, I can see that none of them are smaller than 4.50 or 4.78 or 4.79. In fact, I have to get all the way up to 5.41 before any of them are smaller than it. And there's just the one. 5.70 has this one and this one that are smaller than it, so that's 2. 6.08 has 1, 2, 3, 4 smaller than it. And then 6.21 has 1, 2, 3, 4, also 4. So that's the first step here. And then we're going to add up the number in each column. This is part of the procedure here. Let me just zoom out a bit. We're going to add up the total in each column. So the left side adds up to 53, and the right side adds up to 11. Now we call these two quantities K1 and K2. But they themselves are not the test statistic. The test statistic is actually going to look like this. US is the maximum of K1 and K2, whichever the maximum is. And it turns out that's just 53 for our numbers. So 53 is our test statistic. And we're going to be taking this again to the table for the Wilcoxon-Mann-Whitney test. But before we do that, we need to know some information about what row to look it up on. For this test, that just depends on the sample size in each group. So we're going to call N the sample size in the larger group, and we're going to call N prime the sample size in the smaller group. Now, both of our groups have the same sample size. They're both 8. But if they were different sample sizes, that would be fine. It's just the larger one is N. The smaller one is N prime, and we take that and our test statistic to the Wilcoxon-Mann-Whitney table. So here's the table. Remember we had N and N prime. That's what we're looking up in the row to find out which values to use. So I've got 3, I've got 4. We need to scroll on down. There's 8. 8 for the first sample, and then the other sample size was also 8, so this is the row we're looking at here. And then we're going to find that test statistic that we came up with. It was 53. So you're looking at the bold values to find your test statistic. So you can see I've just circled all those bold values, and our test statistic is 53, so it's going to be between those two middle numbers, the 51 and the 54. So the test statistic is somewhere in here, and so the numbers that are in italics next to the bold tell us the corresponding p-value to the test statistic. So we know our test statistic is in this circled range, meaning the p-value is going to be somewhere between 0.05 and 0.021. So if the test statistic is in that range, 0.021 is less than the p-value is less than 0.05, we got that from the table, then we can say with a usual alpha of 0.05 that p is less than alpha, meaning therefore we do reject the null hypothesis. Or in the context of our problem, there is evidence that suggests that there's a difference in the distributions between the breathing patterns of people in the treatment group as compared to the people in the control group.